This step deals with the compilation of the model. The compilation step is necessary to perform before training the model. It defines the loss function, the optimizer, and the metric. We can compile the model using the compile function, which has the parameters optimizer, the loss function, and the metric. The loss function is a function that measures how closely the model's predictions match the target classes. The sparse categorical cross-entropy loss function is used here, which calculates the cross-entropy loss between the labels and predictions. We use this loss function when there are 2 or more label classes. Please remember we have 20 classes in the segmented MOSC. Then an optimizer is defined for the model. When training a deep learning model, you must adapt every epoch weight and minimize the loss function. An optimizer adapts the neural network's attributes like learning rate and weights. Hence, the optimizers assist in improving speed and performance for training a model and help to get results faster. We will use the Atom optimizer, the best among the adaptive optimizers in most cases. We set the learning rate to 0.001. Generally, a large learning rate allows the model to learn faster at the cost of arriving at a suboptimal final set of weights. A smaller learning rate may allow the model to learn a more optimal or globally optimal set of weights but may take significantly longer to train. Finally, the metric accuracy is defined for the model. This metric is used to monitor how often predictions equal labels and judge your model's performance. Run the code cell to compile the model. Scroll down to the following code cell. Here we define the early stopping callback. You can see the early stopping function which stops the model training in between when your model gets overfitted. This object can perform actions before, after, or during training. Here we need to define the factor we want to monitor using the early stopping function. We will monitor validation loss to stop the model training. In the mode we specify whether the objective of the chosen metric, that is validation loss in this case, is to maximize or minimize. We need to minimize the loss, so we set it as min. The verbose parameter is to discover the training epoch on which training was stopped. Can be set to 1. Once the training stops, the callback will print the epoch number. If the improvement doesn't happen in the first epoch, it may not be the best time to stop training because it might get better sooner. We can account for this by adding a delay to the trigger. We can wait for some epochs with no improvement before stopping training. This can be done by setting the patience argument. Here we set the patience as 20, which means the program waits for 20 epochs before stopping the training. Run the code cell. Scroll down to the next code cell. After that, we define the callback function model checkpoint. This function is used to save the trained model after every epoch. We need to define a few parameters like where we want to store, what we want to monitor, etc. In this case, we will save the best model observed during training as defined by a chosen performance measure on the validation dataset. We have first defined the path where the trained model has to be saved. Here we save the trained model named segment_weights H5 in the image segmentation folder. We assigned val_loss to be monitored. If the validation loss lowers during training, it will save the model in our defined location. Run the code cell. Scroll down to the following code cell. Now that we have defined and implemented our image segmentation project in Python, it is time to train our model. This is the most crucial step. Keras fit function can be used to train our deep learning models. We must pass various arguments into the fit function. As discussed, we must supply the processed image dataset, train dataset for training. The validation data need to be passed as well. The validation data generator and its importance are already discussed. Also, the number of typos or iterations to train the model has to be given. You can also try different approaches and compare the output of the model. Here we provide 25 epochs. At last, we have to provide the callbacks we have already defined earlier. Please remember training is a time-consuming process. The time depends on the size of the dataset and the computing machine. Since you can run the program on Google Colab in GPU, your training will be much faster than on the standard CPU. Run the code cell. Finally, we should now see how the loss decreases epoch after epoch. Please wait for the program to finish training. During training, the best trained model with the .h5ext will be saved automatically in your Google Drive. You can see the file named segment_weights H5 Hereafter, we will access this file for multiclass image segmentation. Scroll down to the following code cell. This is the final and most crucial section of our project. So we have trained our deep learning model and saved the trained model named segmentation H5 in our Google Drive. Now we have to predict segmented masks of custom images. First, we must load the trained model segment_weights H5 by providing the path shown here. Run the code cell. We will predict the segmented masks for the images we loaded in the prediction folder. The model has never seen the photos in the folder during training, which is entirely new to them. Scroll down to the next code cell. Here you have to provide the path of the prediction folder in your Google Drive as shown here. We load the paths of the images in the prediction folder using a for loop. Run the code cell. In the output, you will be displayed the total number of images in the prediction folder. In this case, we have 40 images. We know the mask would have 20 different shades or classes, where each of the 20 channels is a binary mask corresponding to a predicted label. The predicted mask would look visually appealing if the 20 classes in the mask were shown in different colors. We will utilize the human color map for this purpose. All colors on a computer are made up by combining red, green, and blue lights of various trends. We call it RGB color code. Each red, green, and a blue light level is encoded as a number from 0 to 255, which signifies its brightness. In our segmentation mask, we have 20 labels, so 20 RGB codes are needed to represent the mask in color. I have opened the human color map file in the MATLAB software. You can see 20 rows, and each row represents a unique color. You can also notice that each row contains 3 values that represent the RGB values divided by 100. Scroll down to the next code cell. Here we are loading the human color map file, which contains the color details of the 20 classes. You can also keep the color codes in other file formats like CSV, TXT, etc. Whatever the format, the concept remains the same. You have to read the file appropriately. Here we read the file using the loadmap function. You must correctly provide the path of the human color map file as shown here. We would also plot an overlay of the RGB segmentation mask on the input image, as this further helps us to identify the different categories present in the image. More intuitively, in-Keras predictions are carried out using the predict function. At last, we call the helper function plot predictions by supplying 3 arguments: the input image paths for segmentation, the color map for visualizing the prediction in color format, and the trained model. Run the code cell. The program will fetch the images in the prediction folder and utilize a trained model to generate a mask and colorize it using the color map file. The output will contain the segmented mask of all 40 images. Here I am showing only the first image. You can scroll down and see the whole image. The first image is the image that you supplied for creating the segmented mask. The second image is the segmented mask overlaid on the image provided. The third image is the segmented mask. You can see how accurately the trained model predicts the mask. You can also try with different images in the prediction folder. Please remember we have used only 1125 images for training and building the model. The robust algorithm's accuracy can be increased by increasing the number of epochs, training images, and other parameters we have set in the model. You can use the code and modify it according to your application by making alterations. We will meet on another exciting course.